Welcome back to the second part of the video. In this part, we will introduce our first proof technique, proof by contradiction. Here's an overview of what this part will cover. We will first go through the fundamental understandings of how contradiction statements work, and then go through several examples. Citing from the 331 page under Support Materials, we have the formal definition. The negation of P to Q is P and not Q. Note that P and Q are propositional formulas, meaning they are logical statements made up of simple true or false statements connected by words like and, or, and not, to express more complex ideas. We can also read as the negation of if P then Q, or given P, Q, is if P and not Q. Well, why does the negation statement look this way? If you still remember proofs from CSC 191, I encourage you to do the proof yourself. There are many ways to prove it. One way is to write out truth tables for both formulas, and the other way, which I am showing in this video, is an indirect proof. If you are choosing to use indirect proof, a hint will be using De Morgan's law. The definition of this law is that the negation of P and Q is the same as not P or not Q. Similarly, the negation of P or Q is also the same as not P and not Q. Now let's go over the indirect proof. First, we have the starting statement and the ending statement already known. Step 1. To find a negated statement of the original P to Q, we need to first negate the original statement. Then in step 2, we can do a rewrite of step 1 since we know that P to Q can also be written as not P or Q due to logical equivalence. So now we have the negation of not P or Q. After the rewrite, we can apply De Morgan's law on step 2 into not P and not Q. Lastly, we know that double negation is just positive, so we have P and not Q, which is our final negated statement. In words, a good starting point of proof by contradiction is that we take some original statement and negate it, then possibly come up with a contradiction. But be extra careful with relations when doing the negation. A tip will be never negate any given or if portions of the original statement, since that is the given ground truth, which cannot be false throughout the proof. Another tip is that make sure negation of every is there exists one. Swapping them also works. The negation of there exists one is every. As a quick example, say we want to determine the correctness of the statement, "It is raining right now." You may ask, what is the purpose of doing this contradiction when we can directly try to prove the original statement? Well, sometimes if we don't negate the statement and then prove it, we may not realize that our argument has a logical inconsistency within. In other words, using proof techniques can make proofs easier as it acts like a recipe and all you need to do is just follow the steps. To demonstrate this quick example, we will first find a negation, which is, it is not raining right now. Depending on where you are, if you go outside right now and you did not feel any rain, then to you, the negated statement is proved as true, which means the original statement, "It is not raining right now," must be false. However, if you go outside right now and you did feel the rain, then to you, the negated statement is proved as false. This means that the original statement, "It is raining right now," must be true. In both cases, there can only be one statement that is true. From the rain evidence you found outside, you've determined which one of the statements can be true. On the left-hand side, it is an example where you use proof by contradiction to determine the statement that you're trying to prove was actually false. There is no contradiction in the logic though. However, on the right-hand side is a proper proof by contradiction where a contradiction in logic did occur. Yes, not always proof by contradiction leads to a contradiction. If the statement you're trying to prove is false, you can use proof by contradiction as a recipe to verify whether the statement you're trying to prove is true or not. Now let's go through a more mathematically concrete example. Given f of n equals to n and g of n equals to n to the power of 2, function f and g asymptotically grows the same, and that is f of n equals to theta of g of n. You may pause the video and try it on your own. Thinking about whether the statement is true or false may be a good starting point. Also, remember to correctly negate the statement. Of course, one can use limit definitions to do a direct proof on this example, but we will use proof by contradiction approach for this video's purpose. So let's go ahead and prove the example with contradiction. The first step is to define all necessary subparts, which are P, Q, and not Q. For P, or the given, we have f of n equals to n, and g of n equals to n to the power of 2. Then, we define a non-given part, or q, which is function f and function g asymptotically grows the same, or is f of n equals to theta of g of n. Now, we would go ahead and negate q, which gives us function f, and function g does not asymptotically grow the same. Note that here we are only taking negation of q and not the given p. Also, we can only say that function f and g do not asymptotically grow the same for the negation of q for now, since we are not sure what is the asymptotic relationship between f and g yet. When we have all our subparts defined, we can go ahead and create our negated statement. Given f of n equals to n, and g of n equals n to the power of 2, function f and function g do not asymptotically grow the same. Do notice that the AND between P and not Q can be replaced by a comma, as they logically mean the same. We will then prove this negation statement rather than the original statement in the problem. If some of you are lost at this point, the big hint is that in this example, we will eventually prove the original statement as false. Using the limit rules we learned earlier, we have the limit of n to infinity of f of n over g of n. Plugging in their relative expressions gives us limit of n to infinity of n over n to the power of 2. Now we will go ahead and evaluate the limit. We will first simplify the fraction, and we have limit of n to infinity of 1 over n, which equals to 0. This means that g grows faster than f asymptotically, making them not asymptotically growing the same. We have just proved that the negation statement is true, so this must mean our original statement is false. Asymptotically, since limit of f of n over g of n gave us 0, it must mean f of n equals to big O of g of n, and f of n equals to small o of g of n. Now let's consider the other case around. We have the same function but different statement to demonstrate a version where the original statement is proved true. Given f of n equals to n, and g of n equals n to the power of 2, function f grows slower than or equal to function g asymptotically, or we can say f of n equals big O of g of n. If we do a quick recap on the previous slides, to define f of n equals big O of g of n, the limit of f of n over g of n should either go to 0 or some constant that is not 0. In asymptotics, it is either f of n equals small o of g of n or f of n equals theta of g of n. Using the same recipe as our previous example, we will list out our p, q, and not q. Our p is a given, which is f of n equals to n, and g of n equals n to the power of 2. Our q is f of n and g of n does not asymptotically grow the same. Specifically, f of n equals big O of g of n. Lastly, our not q is f of n asymptotically grows faster than g of n. Specifically, f of n equals to small omega of g of n. Note that it is an only a small omega because big O already includes the data definition, so the negation cannot include so. Analogy is that the opposite of less than or equal to is greater than. This gives our negation statement. Given f of n equals to n, and g of n equals n to the power of 2, f of n asymptotically grows faster than g of n. Specifically, f of n equals to small omega of g of n. To not go over the same limit proof again, we will use the proof in the previous example. We know that the relationship between f and g can be both f of n equals big O of g of n and f of n equals small o of g of n, as proved in our previous example. This means that our negation statement of f of n equals small omega of g of n is indeed false, making our original statement true. As in this example, there is indeed a contradiction in the logic. Thus, we have finished our first proof technique, proof by contradiction. It is strongly recommended to create your own examples and feel how the logic twists throughout the proof. So this is all I have for you in part 2 on proof by contradiction. If you have any questions, do not hesitate to ask on Piazza or come to our office hours.